Welcome back to Calc 3. We're going to go back to Chapter 14 today and finish up the last two sections we're going to cover from Chapter 14. And in 14.7, we're going to talk about extreme values and saddle points. That should be and. So before we talk about multivariable functions, let's go back to Calc 1 and talk about a function of a single variable. Here's our function of a single variable. You could find a local maximum, which was, this would be a local maximum here, if it was the largest function value in an open interval near that point, right? So if I look close to this point, look just around it, this is the largest value. If I look overall, there might be other function values that are larger, but just in a small area, this is the local maximum. The same thing for a local minimum. If near this point, this is the smallest function value, so I go left or right, and the function's getting larger, then this is a minimum. To find these local maxes and mins, what we did was we took a first derivative, and wherever the first derivative was 0 or the first derivative didn't exist, we called that a critical point. These local max and mins can only occur at critical points. So we would look and see, okay, well, if this is differentiable and the first derivative is 0, that means I have horizontal tangent lines, right? And that's what happens when you have a local max or a min. Then we use the second derivative test to figure out which it was. So here, our second derivative would be negative, telling us that our function is concave down. Our first derivative would be 0, telling us we have a horizontal tangent, therefore this is a local max. Here, our second derivative would be positive, telling us the function is concave up. Our first derivative is 0, we have a horizontal tangent, therefore this must be a local minimum. In Calc 1, you also said if you had a continuous function over a closed interval, then you could find the absolute minimum and maximum. In other words, if that function is continuous on a closed interval, it has to attain its maximum and minimum somewhere on that interval. So that's what we have here. We have a function starting at this point to that point, and it's continuous, and I can find its absolute max and min. First, I look at the local max and min and say, well, is one of those either largest overall or smallest overall? And here it is. This is the absolute minimum. It happens to coincide with the local minimum. This is the smallest function value overall on this interval. But the absolute maximum is attained at this endpoint of the interval. And this is the largest function value overall. All of these ideas have their analogs with multivariable functions, and that's what we're going to talk about in this section, and specifically only for functions of two variables. So first, some definitions. A function of two variables has a local maximum at a point a, b, if the function values in a disk around that point are smaller than the function values at a, b. So think we have some disk here, and at the middle we have f of a, b. If that's the largest function value in that disk, so we have kind of the top of a hill, then that is a local maximum. Similarly, for a local minimum, you could think we have some disk, and in the middle, that's kind of the bottom of a cup or the bottom of a bowl, then that's going to be a local minimum. So the function value at the center of that disk is smaller than all of the surrounding function values. Now, if we want to consider absolute maxes and mins, absolute extrema, we just go back to these two definitions and say, okay, I have an absolute maximum if this inequality holds for every single point in the domain. So then this is the largest function value overall. That's an absolute maximum. This is an absolute minimum if this inequality holds for all points in the domain. So this is the smallest function value overall. Okay. So what do these things look like for functions of two variables? If we graph them, we get surfaces. So here's an example of a function with a local minimum at this point. And similar to a function of one variable, at the local maxes and mins, you got horizontal tangent lines. Here we get horizontal tangent planes. Here's another function where I have two local maximum, and one is larger than the other. And you see at each of these points, I could draw horizontal tangent planes. Here I have some other point that I can draw a horizontal tangent plane, but it's neither a maximum nor a minimum. So what's happening here? We'll talk about that in just a minute. But first, let's define what a critical point is. For a function of two variables, we have a critical point if I take partial derivatives of the function at that point, and the partial derivative with respect to x and the partial derivative with respect to y are both 0, or one of them or both of them are undefined. So another way of thinking about this is I have a critical point of this function if the gradient is equal to the 0 vector or the gradient doesn't exist. Now, similar to functions of one variable, if I have a local maximum or a local minimum, then they can only occur at critical points. In other words, if I have a local max or a min, then either the gradient has to be 0 or the gradient doesn't exist. So this theorem is saying if these partial derivatives do exist, and I have a local max or a local min at the point AB, then both of these derivatives have to equal 0. So local maxes and mins can only occur at critical points, but not all critical points are local extrema. Not all critical points have to be maxes or mins, and that's what we see here. This point, if we look at the xy coordinates of this point, not the function value, the xy coordinates give us a critical point here, but that's not a max, that's not a min, it's not a local extrema. What is it? Well, we can see a similar thing happening in this drawing, that I have some point. I could draw a horizontal tangent plane at that point, but if I look in one direction, it's a minimum. If I look in another direction, it's a maximum. So overall, it's neither. It's not a maximum nor a minimum of the surface. That's called a saddle point because it's at the center of this somewhat saddle-looking shape. If we go back up here, you see this is also kind of at the center of a saddle-looking shape. In one direction, it could be considered a minimum. In another direction, it could be considered a maximum. That's a saddle point. All right, let's continue by looking at an example. I want to find all of the critical points of this function x squared plus y squared minus 2x minus 6y plus 14. So first, calculate the partial derivatives. So I take a partial derivative with respect to x, I get 2x minus 2. Take a partial derivative with respect to y, I get 2y minus 6. And now these first order partial derivatives, they're both continuous and they're both defined everywhere. So I don't have to worry about these things not being defined anywhere. So the only place I'm going to find a critical point are points that make these both 0. So I set them equal to 0 and I solve. If I set these equal to 0 and solve, I'm going to get the x equals 1 and y equals 3. If I put these two coordinates together, I get my critical point. The point 1, 3 is a point that makes both of these partial derivatives 0, so it makes the gradient 0. Now I have this point 1, 3, but what I don't know is this point the location of a max or a min, or is it a saddle point? I don't know. I need more information. Where in Calc 1, we went to the second derivative test. We're going to do the same thing here, but it's going to take on a different form. So for a function of two variables, the second derivative test, we have to have a function whose second order partial derivatives are continuous at this point that we consider, and we need this point to be a critical point, meaning that the first order partials are 0. If this is the case, then we define this function d at the critical point, and this function is equal to the second order partial of f with respect to x at the point times the second order partial of f with respect to y at the point minus the mixed order partial, so take a partial derivative with respect to x, then take a partial derivative with respect to y, evaluate at the point and square it. This is called the discriminant. And this is going to help us decide whether we have a max, a min, a saddle point, or perhaps it's not enough. So first, if the discriminant is positive, and the second order partial derivative with respect to x at the point is positive, then we have a local minimum. Now what is this saying? If the discriminant is positive, then that means both of these partial derivatives have to have the same sign. Right? That's the only way I can get something positive. If these both have the same sign, then this product is positive, and I'm subtracting something positive, so it could still be positive or negative. But if I consider the other, if these partial derivatives have opposite signs, then this product has to be negative. I'm subtracting something positive, this entire thing is negative. So in order for the discriminant to be positive, these have to have the same sign. So I'm looking at the second order partial with respect to x, but if the discriminant is positive, this is going to have the exact same sign as the second order partial with respect to y. So you could also look at this, either one. And so if this second order partial is positive, this is kind of saying that my function is concave up in an x direction and is concave up in a y direction. So this is kind of similar to the second order, the second derivative test for a function of one variable. It's kind of concave up in an x and y direction. It's a local minimum. Similarly, if the discriminant is positive and this second order partial is negative, this one would also be negative, then that value is a local maximum. If our discriminant is negative, then this value is a saddle point. And we don't need to check any other information. All we need is the discriminant to be negative. We have a saddle point. If the discriminant is 0, we don't have enough information, so the test is inconclusive. Okay, if we go back to our example, we had our critical point 1, 3. Is this the location of a max, a min, or is it a saddle point? Well, if we go back to our first order partial derivatives and take more derivatives, so I take a derivative here with respect to x, I get 2. Take a derivative here with respect to y, I get 2. Take the mixed order partials, they're both going to be 0. And that's exactly what I have written here. Then I can compute the discriminant. So I multiply these two, I get 4. I subtract this value squared, I still get 4. That's positive. And then I look at this second order partial. This is also positive, so I'm falling into this first category. It's a local minimum. So that means that the 0.13 is the location of a local minimum. It's not the local minimum itself. The local minimum is what you would get if you plug 1,3 back into the function, which was way up here. And if you plug 1,3 back into this function, you'll get 4. So the local minimum itself is 4. 1,3 is the location of the local minimum. Now, if we look at a graph of this function, we will see that we get a paraboloid, right? So this is x squared plus y squared minus 2x minus 6y plus 14. Here's where y is 3. Here's where x is 1. So the bottom of this paraboloid is the 0.13, and we can see we do get a minimum of 4 there. So it's at the bottom of the paraboloid, it's a local minimum. You can think of the discriminant as a 2 by 2 determinant. If you create this array where you put the second order partial derivatives with respect to x and y on this diagonal and the mixed partial derivatives on the anti-diagonal, and we compute the determinant here, which means I multiply partial derivative with respect to x twice times the partial derivative with respect to y twice, subtract the product of these two terms, the mixed partials. This is what I get. And now we assumed that the second order partials of this function were continuous. If I have continuous partial derivatives, then the order I take the partial derivatives doesn't matter. These two are exactly the same. That's Clairaut's theorem. So then I can rewrite this as the mixed partial squared. So the partial derivative with respect to x and then y squared. And this is exactly the discriminant. So it's another way to calculate it. Now let's finish this video with another quick example of finding critical points and classifying them. So I have another function here, x to the 4th plus y to the 4th minus 4xy plus 1. If I want to find the critical points, the first thing I need to do is take the first order partial derivatives and see where they're not defined, or set them equal to 0, rather. Well, if I take the first order partial derivatives, the derivative with respect to x, I get 4x cubed minus 4y. Partial derivative with respect to y, I get 4y cubed minus 4x. These are both continuous for all of R2. So I don't have any points for which this is undefined. So now I just need to set these equal to 0 and solve. And if I do that, what I'm going to end up with is these two equations, y equals x cubed and x equals y cubed. And I need to find all the points that satisfy both of these equations. In other words, if I were to think of these as curves, I would need to find all the places where these two curves intersect. Well, really what I'm doing is solving a nonlinear system of equations. And that can be more difficult than linear equations. There's no straightforward procedure, as in linear equations, lots of different things can happen. But this system isn't too bad. We already have something solved for y, so we can just use substitution. Say, okay, if y equals x cubed, just plug x cubed in for y here. So I get x equals x cubed cubed, which is x to the 9th. And then I subtract x, and I get x to the 9th minus x equals 0. From here I need to factor this so I can solve it. So first I just factor an x out. That leaves me with x times x to the 8th minus 1. But this is a difference of squares. So I can factor this again into x times x to the 4th minus 1 times x to the 4th plus 1. But I have another difference of squares, so I can factor this in the same way. A sum of squares I can't factor. I just leave this the way it is. So I factor x to the 4th minus 1. That gives me x times x squared minus 1, x times x squared plus 1 times x to the 4th plus 1. I have another difference of squares. So I factor one more time to get the completely factored form. X times x minus 1 times x plus 1 times x squared plus 1 times x to the 4th plus 1 equal to 0. If this is equal to 0, that means at least one of these factors is 0. These two are never 0 for real numbers. If I want to solve these, the answers are going to be imaginary numbers, and we're not going to deal with those. So instead I say, okay, one of these factors has to be 0, so x is either 0, 1, or negative 1. So now I have three x values. To find the critical points, I need the y values. I can go back to this equation, plug in what I got for x, and see what y has to be. So if x equals 0, y equals 0 cubed, so y is also 0. If x equals 1, y is also 1. If x equals negative 1, y is also negative 1. So I have three critical points, 0, 0, 1, 1, negative 1, negative 1. Now to figure out what these critical points are, I need to calculate the discriminant. So I go back to the first order partial derivatives. Here I take a partial derivative with respect to x. I'm going to get 12x squared. Here I take a partial derivative with respect to y. I'm going to get 12y squared. And to calculate the mixed partial, I can either take a partial derivative here with respect to y or a partial derivative here with respect to x. They should be the same, and they're both negative 4. So here's what I just said. To calculate the discriminant, I multiply these two, I square this one, and I subtract. So the discriminant is 144x squared y squared minus 16. Now I plug in each one of these critical points into this function and see what the result tells me. So if I plug in 0, 0, I get 0 minus 16, which is negative. So 0, 0 is a saddle point. If I plug in 1, 1 here, that's going to give me 144 minus 16. I only care about the sign of this. I could do the subtraction and say, okay, this is 128 and it's positive. But you can just look at this and say, okay, this is obviously positive. That's all I care about. Then I go, if it's positive, I need to go and look at the second order partial with respect to x. I plug in 1 here. This is also positive. So that means I have a local minimum at that point. The same thing happens when I plug in negative 1, because I'm always squaring these coordinates. So if I plug in negative 1, I also get 144 minus 16, which is positive. For the second order partial with respect to x, I'm going to get 12, which is positive. So I have another local minimum occurring at the point negative 1, negative 1. Now if I look at a graph of this function, you can see that here. X to the 4th plus y to the 4th minus 4xy plus 1. You can see I have two local minimum. There's one here, there's one here, and I have a saddle point. So the saddle point you can see in one direction, it's a maximum of the function. And if I look at a cross section, so if I look down inside of this thing, if I look in this direction, it's a minimum of the function. So I have a saddle point there. All right, and that's going to be it for this video. In the next video, we'll talk about how to find absolute extrema.